Okay, so welcome back to another video. So in today's video, we actually got another integral. So the integral from 0 to infinity of log base e of sine theta divided by a squared plus theta squared d theta for a it can be any real number, but also don't forget that theta cannot be equal to 0 with every periodicity of 2 plus or minus 2 pi otherwise, because sine of 0 is 0 and you can't have the log base of e 0 because that would be undefined. So this integral is nice. It's actually, you could say it's an old school integral from that was used in the in one of the exams in Cambridge University. So I thought that in today's video we actually just evaluate this old school integral, even though I said that twice, but like I think this looks pretty interesting to solve. So let's actually solve this together. Log base e sine theta, we know that's actually just the equivalent of the natural log of sine theta. So I can just replace that. But before I do any of this, let's actually convert sine theta into terms of the exponential complex function. So the natural log of sine theta, that's simply equal to the natural log of e to the I theta, and then subtract that with e to the negative I theta, and then divide that by 2i. And now I'll manipulate the inside argument. So what I'll do is that I'll actually multiply and divide an e to the I theta. So when we do this, for both the numerator and denominator, of course. So when we do this, we get that the numerator is e to the 2i theta, and then subtract that with 1, and then we divide this with, so we'll just leave it as e I theta, and then multiply by 2i. So what I can do is we can actually, using our rules of natural logs, we can actually write this with some addition and subtractions of natural logs. So what we do is that we'll actually get the following. So it's the natural log of, since we have the numerator, I'll just leave it as, well, it's supposed to be 2 to the power 2e, e to the power 2i theta minus 1, okay? And then subtract that with ln of e to the I theta, and then also subtract this. I'll separate the 2 and the I, so that means I'll have ln of 2, and then subtract that with the natural log of I. So with this, I can simplify some things out. Really, it's just these two terms over here specifically. So we have the natural log of e to the 2i theta, subtract with 1, and then minus, so the ln of e will cancel, so we're just left with I times theta, and then minus ln of 2, and then minus, let's see, ln of I. So what you can do is you can actually expand the complex logarithm to find your value of I. Either that, or you can actually use your analytical skills with the polar form, and you'll evaluate that ln of I is actually just simply equal to I multiplied by pi divided by 2. So now what we can do now is simply just looking at this, our first term here, what I can do is I can actually factor out e to the power 2i theta from our inside input. So it's e to the 2i theta, that's multiplied with 1, and then subtract that with now e to the negative 2i theta, and then we still have our same terms from over here. So I theta minus ln of 2, and then minus I times pi divided by 2. So now expanding further using natural logs again, so now I can actually write this as a sum of two natural logs. So this will be the ln of e to the 2i theta, then plus ln of 1 minus e to the negative 2i theta, and then with our other terms as well. So negative I theta, ln of 2, and then I times pi divided by 2. And so now simplifying some terms out, you'll see that ln of e to the 2i theta, that's just going to cancel with the base, so we're just left with 2i theta, but then also subtract with I theta, so we'll just get a positive I theta, and then that's the only thing we can do for now. So I'll just rewrite what we're left with currently. So let's see, so this will be a plus I theta, and then this will be ln of 2, and then minus I times pi divided by 2. So now let's actually separate the terms out. So we actually have a complex number. So we'll separate with x being our complex number z equals x plus I times y. We'll separate it so that x equates with the real part and then y equates with the imaginary part. So with this, we have the natural log of, 1 minus e to the power 2I theta, or to the negative, excuse me, and then minus ln of 2. I'll just put a bracket just to denote some equivalent parts. So, and then now the imaginary part, which is just I theta, and then subtract that with pi divided by 2 using our black pen. So over here, this is actually the real part, which of course we want to show. So this is the imaginary, and then this is the real. So we want to solve for the real, okay? So now what I can do is, because simply what we're trying to solve is we want to solve for the real parts of this integral, so we equate the real parts. So now jump into the next step. Here's a little thing that we're going to note here. So here's a little fact, and you've seen this like countless times in videos, but we're actually going to be using a little Taylor series expansion. So I want to note that so the natural log of 1 minus x, let's just call that variable x. We know that the Taylor series expansion is simply just equal to the negative infinite sum, starting with our index from n is equal to 1, of x to the power n and then divided by n. Using this little fact here, I can actually rewrite our ln of 1 minus e to the power negative 2I theta into the Taylor series form. So using this, let's see, so ln of 1 minus e to the negative 2I theta, that's simply just equal to negative, let's see, the infinite sum, n is equal to 1. And so I'll just plug x with our e to the negative 2I theta, so negative e, and then, or that's supposed to be a positive e, whoopsies, e to the negative 2I theta, and then divided by n. Okay, n to the power n, don't forget that. And then we can actually use a little property called, in complex analysis, with the Euler's formula expansion, de Moivre's formula, meaning if you have the polar form and then the exponent is to some n power, so you can actually distribute the n to the input of the Euler's formula. So let me first use our rules of exponents and just distribute the n into here. So let's see, n is equal to 1. So we get that this is e to the negative 2I n theta divided by n. And then expanding this out, we get that this is negative, let's see, the infinite series, n is equal to 1. So we get that this is cosine of negative 2n theta, okay? And then plus I sine negative 2n theta, and then all this being divided by n. And so I want to, again, we're trying to equate the real part. So when we're finding the real part of this Taylor series, we're actually just looking at the cosine of negative 2n theta, but cosine's an even function, so that means the negative will just cancel itself out. Not here, I mean, but like just the input I'm talking about. So this means we have infinite series, n is equal to 1 of cosine of 2n theta, and then divided by n. So let me just justify this piece over here saying that we want to equate the real part. We have that the final, well, not really the final, but what it comes down in terms of simplification is that the natural log of sine theta simply is actually just equal to, let's see, the negative infinite sum, n is equal to 1 of cosine of 2n theta, then divided by n, and then subtract that with our minus ln of 2. So that's also equated with the real part of this integral. So that's what it comes down to. And so now we have that, so we can actually substitute our our log base e of sine theta, or well, the natural log of sine theta. Okay, and so I'll move it to over here. Right here is fine. So from this integral, so our new integral so far is that, and also because this is also convergent, so I can actually just move the sum outside of our integral. So this means I can also rewrite this as, let's see, n is equal to 1. And so we have 1 over n. We have 1 over n. We're about to integrate in terms of theta, so I'll just move that outside for now. And then multiply with our integral from 0 to infinity of cosine of 2n theta. And then divide that by a square plus theta square. And then we'll d theta, but also subtract that with our natural log of 2. So this is the integral from 0 to infinity of, well, okay, natural log of 2 is a constant, so really I can just move this outside. So the natural log of 2, and then our integral from 0 to infinity of 1 divided by a squared plus theta squared d theta. Yeah, simply just because we substitute our series, or well, not really a series, but the evaluated simplification of natural log of sine theta, but you also distribute the 1 over a squared plus theta squared into everything in here. That includes the natural log of 2. So that's how we got this integral as well. That's easy to show, but I'm gonna skip this step later because right now what I really want to focus on is evaluating this integral over here. Okay, so like what we want to pay attention is that notice that this function over here is it's even because you can plug negative theta into here. You're gonna get the same thing. So what I can do is I can actually rewrite this integral as the following. So then we actually can write this as 1/2 multiplied by the integral from negative infinity to infinity of the same integrand. So now what I want to do is we're actually gonna jump into the world of complex analysis and consider a complex value function. And I'm sure you can actually take a guess from here, but we're going to be using the residue theorem. So from over here, I'm going to suppose that f of z is equal to e to the power 2inz and then divided by a squared plus z squared. Where did I get e to the 2inz? Simply because if you expand its polar form, you're going to get that using from Euler's formula, you're going to get cosine of 2n theta plus I sine I times sine 2n theta. And we're dealing this with complex numbers in terms of c, but you know, it's another simple way to consider the complex function simply when we started off with the real parts. So we want to consider both the real and imaginary parts to calculate the residue from there before we can actually do any sort of equating. You'll see that now, like I said, we're actually going to be using residue theory, the residue theorem to calculate our poles to actually evaluate this integral. So what you'll notice is that over here is that e to the 2inz. If you take a look at the denominator, you can actually expand this from the difference of sums, and you'll get that this is just a, or rather, I'll write it like this. I'll put the z squared first and the a squared last. So this can be decomposed as z minus I times a, and then z plus I times a. Okay, and then you'll see that our poles is simply just equal to z is equal to plus or minus I times a. Okay, now before we do any of this, I actually want to break this into a contour integral. So give me 1 second to sketch our little contour, and I'll come back into more discussion. Here's our little contour, capital gamma. So the way I define this is we have a contour evaluated from negative r to r. So simply, because we have negative infinity to infinity, I'm going to write this in terms of limits such that r is approaching infinity. But we can also define a semicircle arc. I call that lowercase gamma. And so we can actually break this into two contour integrals. So we're integrating along the x-axis, and we're also integrating alongside this semicircle arc, lowercase gamma. So simply, when we actually write this contour integral, we get that the formula is that the integral over the whole contour capital gamma of f of z dz is equal to the first, the limit as r approaches infinity from our integral from negative r to r of now f of x dx. And simply we're just evaluating on the x-axis line. Should write that this is x, and over here this is I times y. And then we add this with our integral over the semicircle arc. So that means this is lowercase gamma of f of z dz. This is important to say because like I said, we are using residue theory, so we have to calculate our poles, but we need to see that where our poles lie. Do they lie inside the contour or not? And we show that right here using our sketch of the contour. We see that positive I times a falls inside that contour, so it is the only pole we need to calculate since negative I times a lies outside of the integral. So we can just completely ignore the pole at z is equal to negative I theta and just calculate the residue at positive I theta. So I'll also write that our residue formula, so I'll put it this way. So over here we have again the same contour. So gamma f of z dz, that's equal to 2 pi I, and then multiply with our sum from n is like however many poles there are, and then j is equal to our first index of the residue of f of z, and then at our pole z of j, z sub j. And then also the residue f of z zj is simply just equal to the limit as z approaches zj of z minus zj multiply with f of z. Okay, so we have those formulas down, so now we can calculate some stuff from here. The only pole exists is the positive I times a. So really, we just need to calculate our residue at f of a. So let's see, so over here, good, yeah, okay. So the residue at f of z at positive IA is equal to, let's see, so this will be the limit as z approaches IA of, let's see, so if I plug z minus zj, so our zj being the one and only pole at positive IA, you'll see that this is going to cancel with this piece of this factor over here, so we're left with z plus IA on the denominator. So evaluate this, so this means this will be, let me just erase the limit here and just put the valuation. So we have e to the power 2in of IA, positive IA, and then IA plus IA, where, okay, we evaluate this, we get that this is e to the negative 2na, and then divided by 2ia. So we have that established, and then I'll just underline that's our residue. That's just our residue for now. We're not done completing the stuff yet. Okay, so we found our pole, so that's good and out of the way. So let's actually go back to this the breakdown of our contour integration over here in this orange. So I want to find what what's the value of the semicircle arc at f of z. So okay, let's just define some parameterization. Z theta equals capital R multiplied by e to the power I theta. So we use that, and also don't forget that theta is actually in the interval between 0 to pi. It's the closed interval. But you'll start to see that we can actually apply Jordan's lemma, and you'll see that as r approaches infinity, then the integral of the semicircle arc is actually just going to equal 0. Okay, so this means this term's just going to equal 0, and so the only thing left we have to evaluate is just our limit along the x-axis. So now really we have that the integral from f of z dz is equal to, so let me see where we're at. So over here, so I'll just plug our bounds back for infinity. So this is infinity, negative infinity of e to the power 2inx, and then divided by a squared plus x squared dx. And so we can actually equate this with our residue theory theorem. So let's see. We calculated that the residue is equal to e to the negative 2 na divided by 2ia, but forgot to multiply the 2 pi I to that. So let's see, e negative 2 pi a, or pi, it's supposed to be n. So negative 2na, and then divide that with 2ia. So some terms will cancel, so the 2 and the I will cancel, and so we get just pi divided by a, and then e to the negative 2na. Okay, so we know that this equation is equal to this equation. So now if I were to expand this out using Euler's formula, so okay, so going back to here, this means this is cosine of 2nx and then plus I sine of 2nx, then a squared plus x squared dx. Simply, if I just equate the real part, so because that's also a real number too, then really it's just infinity, negative infinity, and then just cosine of 2nx divided by a squared plus x squared dx. This is just equal to just pi divided by a, and then multiply by e to the negative 2na. Okay, but from over here we said that we were given that we were given 1/2 times this integral. So what this means is that 1/2 of this integral means I have to multiply the 1/2 to the other side. So to put it simply, I'll write it in this way. So we're given this. We're given given from the integral from over here 2n what is it, theta, then divided by a squared plus theta squared d theta. If I actually just multiply the 2 to both sides, so for one, this will get rid of the 1/2 on this side, and this will actually multiply with the 2 from our half integral of the same integrand. So this will be 2 times the integral from 0 to infinity of cosine of 2n theta, and then divided by a squared plus theta squared d theta. And so all that's left is you just divide the 2 to both sides from here, so we get that this is just pi divided by 2a, and then e to the negative 2na. Just underline this. Let me just also justify by saying divide 2 both sides from here, otherwise I don't want to make it look divide by 2. And so now going back to our sum over here, so we have negative the infinite sum from n is equal to 1 to infinity of 1 over n of our it's just basically the same, this are given from earlier, so theta, from 0 to infinity, cosine of 2n theta, and then divide this by a squared plus theta squared d theta. And don't forget, we actually have to evaluate the minus ln of 2, and then the integral from 1 or 0 to infinity of 1 divided by a squared plus theta squared d theta. But like I said, that's not hard to show. In case you don't know, that's actually the antiderivative of its antiderivative is actually just arctangent. Or here, okay. So before I jump any further, let's actually evaluate this. So it's just using our rules for the antiderivative. Arctangent is basically just 1 divided by a, and then multiplied by arctangent of theta divided by a. But I can actually just multiply the natural log of 2. So let me put this over here. So we get that this is actually ln of 2 divided by a, and then arctan of theta divided by a, evaluated from infinity to 0. But arctangent of 0 is just 0, and then arctangent at infinity is actually just equal to pi divided by 2. So you multiply that, so we get this is pi multiplied by ln of 2, and then divided by 2a. Okay, now moving on, now we have the pieces we need. So now we can actually continue further simplification from here. So this means we get that, notice that they actually both share a pi divided by 2a, so I'll actually factor that out. So we get that this is, still writing in orange, it's supposed to be black for this one. So this is supposed to be negative pi divided by 2a, and then multiply with the infinite sum of, so let's see, this is from, okay, so e to the power negative 2na, and then we divide this by n, since that's coming from the 1 over n from over here, so I just distribute to that, and then just subtract that with the natural log of, so I didn't actually factor out the pi over 2 yet. I just want to write out some stuff first before we actually do the factoring. So let me do that first. So, okay, so this is what we have so far. I just moved the pi over 2a to outside of that, since this is just because it doesn't depend on this series, since it only depends for n. Okay, and now from here, now we can actually do some, well, okay, not really factoring yet, because what we can do here from this sum, we can actually use that definition of the Taylor series over here and rewrite this back. So now we have that this is pi divided by 2a, or negative pi divided by 2a, and then multiplied by the natural log of 1 minus e to the power negative 2a, and then subtract that with pi divided by, or pi times ln of 2 divided by 2a. And then the rest is easy to show from here. We factor out the pi divided by 2a and then combine with the natural log rule, since they both share the natural log. We get that the final answer is actually just equal to pi divided by 2a. Oh yeah, also another thing, I forgot to put that this is supposed to be a positive over here, so that cancels. Okay, because yeah, that throws you off sometimes. Just keep that in mind. So we get positive. So now the final answer is that we have pi divided by 2a multiplied by the natural log of 1 minus e to the negative 2a divided by 2, like so. And there we have it. The proof has been complete, or rather, we solved for our integral given in this orange box. All right. Now that's pretty cool if you ask me.